in a small telescope, one of the most striking things that you notice about Jupiter is that it's got stripes on it. Now this picture right here was one of the Voyager pictures that have been enhanced a little bit to show details more, but just a small amateur telescope will show this. Now the stripes don't always look the same. Sometimes they're more prominent, sometimes they're less prominent, so they change a little bit. Some years ago, the southern stripe, the one in the lower right on this picture right here, actually disappeared altogether. And so it just looked really weird, Jupiter just having one stripe across it, one band. And then the other times I've seen the northern band fade. I've seen both of them fade. Sometimes I've seen both of them get extra bright or extra dark at times. What's going on is that those bands are caused by cloud layers. Now, Jupiter in the deep interior is hydrogen, helium, you got ammonia, you got ammonium hydrosulfide, you got water vapor, all these sort of things in there. But just like with Venus, at certain distances from the center of the surface, center of the planet, then the pressure is going to be different. So the higher you go, the lower the pressure, and the temperature is going to be different. So typically the higher you go, the temperature is going to drop. So at some point, then what happens is that the temperature and pressure are just right to allow clouds to form. The kind of clouds you get are going to be highly dependent on the temperature. Okay, so at lower levels, it's going to be warmer. So this graph here shows temperature with elevation here, and the higher you go, then the cooler it gets. So you end up with a layer here in which the temperature is warm, as warm as it is on the surface of the Earth, and down to like close to freezing or below. And in this realm in here, you can get water clouds. So you can either get water vapor clouds, sort of like the water vapor clouds we have on Earth, or ice clouds, something like the higher altitude clouds we have on Earth. But again, it's water type clouds. Now, as you get higher and higher in the atmosphere, the pressure gets less and less, and the water vapor clouds become a little more difficult to get, but and the temperature gets lower, and so at some point you get up here and the temperature is really very low, and so this is like dry ice temperatures almost, and at that temperature you get the ammonium hydrosulfide clouds. And so the ammonium hydrosulfide clouds are going to be a different color than the water clouds. Water clouds typically reflect all different wavelengths of light, and so they tend to be white. The ammonium hydrosulfide clouds reflect the longer wavelengths more, and so they tend to be darker in color. And then when you get really high in the atmosphere, the pressure is really quite low and the temperature is extremely low. So the temperature is way below the temperature of dry ice. And at this point, you start getting ammonia clouds. And so ammonia ice crystals and so forth. And so you get ammonia clouds at that point. And so the ammonia clouds reflect light very well. So they're going to make it white again. So kind of like the water vapor clouds. And so those are the different cloud layers. What happens, though, is because it rotates so fast, the planet rotates so fast, then the coriolis force is extremely great. You remember how we talked about on Earth, we have convection. We got air coming up, air going down and circulating, and because of the coriolis effect, we have trade winds that blow in one direction or the other. Well, on Jupiter, the Coriolis effect is going to be so great that these winds are blowing like almost parallel to the rotation. And so where the air is sinking, you don't get a whole lot of clouds up at upper elevations. Where the air is rising, then it condenses to make clouds up where it's very, very cold. So the zones here, the zones are going to be those ammonia clouds that are very, very high altitude clouds. And so those are those ammonia clouds that are very high altitude. That's going to be giving you those zones. The belts or the bands, and again, depending on who you ask, the terms are interchangeable. So the belt or the band, you're actually seeing through clear air at upper elevations into clouds at lower elevations. And those clouds are going to be the darker colors. And so that's what we see here. And this is actually an infrared view of Jupiter. And so in the infrared view of Jupiter, what you notice is that at the places where you see the zones, okay, that's going to be dark here. And so the zones are going to be dark because, well, you're seeing regions here. Again, the equatorial zone is going to be dark right there. You see regions where you have these very high altitude clouds, which are very, very cold. They don't give off much infrared. The belts here, though, the belts or bands, you're seeing into deeper layers of the planet. And so at that point, you see, it is actually going to be the darker colors. You're seeing deeper where it's warmer, and so it's shining more in the infrared. And so the belts, infrared, more light giving off because they're warmer. One thing you notice, though, that's distinctive is the great red spot here. The great red spot is kind of one of these darker colors, but it's very dark, it's very cold. It's actually not caused by ammonium hydrosulfide, but rather by other chemicals that are pulled up from deeper in the planet. And so as the clouds are pulled up very, very high, these other chemicals are deposited and make clouds there that are colored as well. This is actually a photomosaic of the view seen by one of the spacecraft coming in towards Jupiter. And I think this was actually the Cassini spacecraft, so it flew past Jupiter, but as it flew in towards Jupiter to get the slingshot pass, you can see the clouds moving, and you can sort of see what's going on here. You can see, for example, in the band or the belt down here, the clouds coming in and swirling around the great red spot that's there. So you see it swirling around the great red spot. You see also some of these festoons up here the boundary between that belt and zone where the clouds are being ripped off of one another, off of one layer into the other, and so you have these little festoons of little wispy things in there, and then turbulence in there as the different motions slide past each other. Again, more storms that are in there. And so Jupiter is an extremely stormy world right here. That's taking a lot of those pictures and stretching them out. So this is a stretched mosaic here. And you can very clearly see the motions of the clouds here and the storms moving past each other and swirling around the great red spot, and some of the little small storms also swirling. And so again, this gives you an idea of the atmosphere and how the atmosphere moves. The great red spot itself is one particular storm. Great red spot is kind of like a hurricane, but it's enormous. It's much larger than Earth. Imagine a hurricane even larger than Earth. And it's a stable storm system, meaning that it's been visible since they had telescopes capable of seeing it. Now, Galileo looked at Jupiter and did not record the great red spot, but it's questionable whether his telescope could have even seen the great red spot. Once telescopes of sufficient capabilities to see the red spot were definitely available, red spot's been there. Now, it's been getting bigger and smaller over the years. It moves around in longitude, so it doesn't go around exactly the same rate the planet rotates. It does not change latitude. It's pretty much stuck where it is in latitude. So it just migrates left and right in longitude, and it tends to be fairly stable. Now, there's a question as to how long it is stable. Is it stable for hundreds of years, thousands of years, millions of years, billions of years? We don't really know. There's some indication it may be stable for a very long time. There's other indications maybe it waxes and wanes over hundreds of years. It also changes in color. The color of the great red spot is due to phosphine gas that's being pulled up from the interior. That gives it sort of that reddish color that it has. Now, the amount of phosphine in there changes over time. And so that means it changes color. It's sometimes a blood red color, which hence the name, great red spot. Usually it's kind of a reddish orange color. Sometimes it's kind of a pale, creamish, pinkish color. Calling it the great pale pink color is not really a very snazzy name, so we keep calling it the great red spot. I've seen it very vividly red before, and I've also seen it fade to the point where it's virtually invisible. Most of the time, it's very difficult to see with a small telescope. Because it is almost the same color as some of the clouds in the background. Now, like I said, I have seen it at times in which it's a very vivid red color and it stands out quite prominently against the southern part of Jupiter. There are other storms there, little white ovals that are little clouds, white storms clouds there. These are also quite large. Some of them can be almost the size of the Earth. And so I say little storms, there's only little compared to the Great Red Spot. By the way, the Great Red Spot has been shrinking over the last decade or so. And some people claim, well, that's just a natural shrinking. Other people claim it's about to go away. I don't think we really know enough to say one way or the other. Now, there's also a handful of really rare storms on Jupiter that are very clear storms, in which you can see straight into the interior of the planet if you would have to be close enough there. Those are very rare on Jupiter, and we don't fully understand them. So again, another graphic coming in towards Jupiter showing the storm. New storms appear all the time. Again, the Great Red Spot isn't always red. I mean, I've actually seen it very, very white once. But the Great Red Spot does change in color, and these other storms just do appear and disappear over time. If you look at Jupiter from equatorial projection here, you see the storms tend to be right along the bound. Most of the storms are bound along the boundaries between the zones and the belts. Some of them are embedded in a ring around the polar regions.